The uncertainty principle was devised in 1927 by Werner Heisenberg. It states that the more we know about a particle's position delta x, the less we do about its momentum delta p along x. It is given by the equation delta x times delta p along x is greater to or equal to h bar over 2. There are two ways of understanding this. The first one is with wave packets. If you just have a single wave, it is delocalized over all space, we don't know where it is at all, but its momentum is known exactly, it's h over lambda. When you add those waves, you obtain a wave packet which is a burst, so you know that the particle has to be within that burst. However, since you're adding different frequencies, you don't know the momentum as well, so you get an uncertainty in momentum. If you have single slit diffraction, you know that the electron has to go through a slit, and the smaller the slit is, the more you know where it is when it goes through the slit. That means that its momentum along the y direction has to increase, and its diffraction pattern becomes more spread out on the screen.
Right, let's move on to the next part, a simple mathematical proof of the uncertainty principle. This is a diagram for the single slit experiment. For this dark fringe, d sine theta is equal to lambda, and then sine theta is equal to lambda over d. According to this small angle approximation, sine theta is approximately equal to theta. Additionally, theta is also the angle between the uncertainty in y momentum and the momentum in x direction. Because sine theta is approximately theta, and it is also about tangent theta. Thus, lambda over d is equal to delta py divided by px. On the right hand side, because the momentum in x direction is also equal to h over lambda, thus lambda over d is equal to delta py times lambda over h. Here we got delta py times delta y is equal to h, and it is greater than or equal to h bar over 2, QED.
This uncertainty principle tells us that we can't measure the speed and position of a relatively tiny particle accurately and precisely at the same time. For example, if we want to decrease the uncertainty in the position for an electron, we'll need to use a photon with extremely high energy. According to E equals hf, high energy here means high frequency, and according to C equals lambda f, the wavelength will decrease. This means we can measure the position for the electron with very low uncertainty. However, the electron will get much larger momentum, and this results in a much larger uncertainty in its momentum.
This is an example to showcase a practical usage of the uncertainty principle. Here, we have the classical atom with a proton in the center and an orbiting electron. As per Maxwell's equations, accelerating charges emit photons, which implies that the electron would crash into the photon because of the fact that it accelerates, and this model would imply then an instability of matter. Using the classical formulas for kinetic energy and potential energy, we find that the energy is infinity when the momentum and the electron-proton distance is 0. Fortunately, we have the uncertainty principle which says that the electron can't have 0 momentum. We define the electron-proton distance to be a, and the momentum is then on the order of h bar over 2a. The energy is then shown to be positive infinity at a equals 0, which implies that one requires infinite energy to bring the electron close to the proton. If we differentiate energy with respect to A and find the minimum value of A by equating the differential to 0, we find that the minimum value is approximately 0.5 angstroms, and the associated energy is minus 13.6 eV, which means that it takes 13.6 electron volts to take the electron out of its orbit. But this is just a model since we choose our values because of orders of magnitude in order to allow our theoretical model to spit out the answer we wanted. Nonetheless, the uncertainty principle prevents the collapse of matter, provides the correct density of matter, and yields the proper binding energy of atoms.
Heisenberg's microscope was a thought experiment he proposed to help visualize the inability to measure both location and momentum of a particle at the same time. He considered an electron as a classical particle. In order to observe it, a photon travelling along the same axis is scattered off it through a lens. The scattering gives the photon a y component of momenta. However, as it passes through the lens, this could lie anywhere between p sine theta to minus p sine theta. We can estimate the uncertainty in momentum using first the de Broglie equation for momentum and the small angle approximation to give 2h theta over lambda. Uncertainty also arises from the lens. The smallest resolvable angle is given by d sine psi equals lambda, where d is the diameter of the lens. From small angle approximation, this gives psi equals lambda over d. We can then determine the following equations from the diagrams. Combining these gives an equation for the uncertainty delta x in the position of the particle. Multiplying the uncertainties and cancelling elements gives the value h, which is similar to the mathematically derived. Although this approach aids in visualizing the uncertainty principle, it is incorrect as it treats the electron as a classical, not quantum particle.